Welcome back to Lecture 10 on the Rotorcrafts. In this Part 2, Segment 2, we will focus on the control of quadcopters. In the previous segment, we have seen that the dynamic model of a quadrator becomes pretty decoupled once we are looking at hover or only small attitude angles. The goal of this segment is to look at the control of a quadrator. So a quadrator has to move in free space, so it has 6 degrees of freedom. However, with 4 motors on quadrators, we have only 4 inputs, so the whole system is underactivated. This means that not all states are independently controllable. So for example, for forward motion, we have to tip the quadrator around roll and pitch. We assume, furthermore, for the control that we have a full knowledge of the state. So, in reality, of course, we need additionally a state estimator. Furthermore, we assume that the motor dynamics is negligible and we are going at low speeds, so only the dominant aerodynamic forces are considered and we can linearize the whole system around small angles of attitude. As we have already seen in the analysis of the dynamic model of the quadrator, the whole system becomes quite decoupled along the different axes when we are close to hover with small attitude angles. In this context, it's also very obvious that we can intuitively understand how we might control in a simple way a quadrator. First, start with the Z control around the Z axis. It's intuitively obvious that by just changing the sum of the all 4 propellers, the whole system will move up or down. Then, of course, we want also to control the rotation around the Z-axis, and this can be actually realized by an imbalance between the 2 rotor pairs. Additionally, for a longitudinal control, forward speed, we can just change the speed of rotor 1 and 3 and automatically the system will tip in and move forward. The same is for lateral control, sideways speed. So we have just to change the rotational speed of rotor 2 and 4 and the whole quadrator will move laterally. In order to simplify the equations for the controller layout and to get a nice decoupling between the different degrees of freedom, we first introduce a virtual control input. For roll, the virtual control input U2 is proportional to the square of the rotational speed of rotor 4 minus the rotational speed in square of rotor 2. For pitch direction, it's exactly the same. You just replace the 2 other rotors. For the yaw direction, the virtual control input U4 is proportional to the sum of all propellers. However, you have to compensate for the sign because 2 of the 4 propellers are counter-rotating. In thrust direction, you introduce the virtual control U1, which is just B multiplied by the sum of all rotational speeds in square. If you do this and plug this into the dynamic equations we have seen before, we get then a simplified description of the whole system where we have also a very strong decoupling with these virtual control inputs. With these simplified models, we can now approach the control of our quadrator. As we can see in the equations, the rotational dynamics is independent of the translation dynamics. So we can actually propose a hierarchical control. So the inner loop of the hierarchical control is the attitude control, which uses the virtual control input U2 to 4 and then controls directly the attitudes in body frame. And the outer control loop is actually using the output of the inner control loop, but additionally the virtual controller of the Z direction is added, and the whole control is then in earth frame. As we are looking to a control layout close to hover, we can further reduce actually the complexity of the system. If you look at the attitude control and attitude dynamics, which is actually concerned with the inner loop of our controller, we have at a very small angle a reduction of the system. So if we start with the dynamic models, which you can see here on the left with the virtual control inputs, this reduces actually to a very simple dynamic model where the roll, pitch and yaw are directly dependent from the virtual control input. So we have then also a strongly decoupled control, and this allows us to have a much simpler way to find an appropriate controller for our quadrotor. The most obvious controller type for our decoupled system is a PID controller. This is very often used, it's easy to tune, and it helps really to understand the reaction of the system towards a controller. A PD controller or PID controller consists of three terms. The proportional term, which is actually giving a feedback proportional to the deviation from the desired angle or position. You have the integral term, which is actually integrating the deviation over time, and the derivative term, which is actually proportional to the change of speed of the deviation. We have seen in your control lectures for sure different ways to tune this, for example, Siegel-Nichols method or post-placement. And because it's widely used, there is a lot of tools on different platforms available for this type of controller. The implementation of a PD controller for attitude control for our quadrotor in this highly decoupled system is now straightforward. We just, in this example for the roll, replace the virtual control input by the feedback PD controller, which is then actually a proportion factor multiplied by the difference between the desired angle, roll angle, and the actual roll angle, plus a second constant for the derivative of the difference between the desired rotational speed in roll and the actual speed in roll. So by plugging in a PD controller for all the three separate attitude control loops, we get very simple control of the attitude of our quadrotor, and additionally we have one thrust input which actually will have an influence on the height control of the system. Of course, once you want to use this controller, you have to have an actual measurement of the roll angles, pitch angle and yaw angles and its derivative. These values are actually coming from the state estimation. The main part of the whole state estimation is coming from the so-called IMU, inertial measurement unit, which gives you directly a rotational speed and accelerations, and in many cases in combination with some external measurements, you can have a very precise measurement of the roll, pitch and yaw angle and its derivative. As mentioned before, for PID controller, there are different tools to tune the parameters of the controller. The most straightforward and simple way is probably to just look at the desired convergence time and the desired damping of your closed loop system. In theory, you can actually have whatever convergence time and damping. However, in reality, it's a little bit different because you have limited actuator dynamics. So the motor to generate a rotational speed. So you have to consider this in your tuning, and you have to be sure that your actuator signal is not putting the motor in saturation. Once we have appropriate controller for the virtual control inputs, of course we have to get it back on the real value, which means the rotational speed of the 4 different rotors of our quadrotor. So how we can do this is as followed. First of all, we write the virtual controller input and the relation with the rotational speed in matrix form. And then we actually invert this matrix and we get actually a relation between the virtual control inputs and the real rotational speed you want. And this matrix, which is then called allocation matrix, allows you to very fast convert or transform the virtual control input to real motor speeds, which are actually what you can control. So you have then these different elements of this matrix you can actually easily calculate from the definition of the virtual control inputs we have seen before. With the decoupled control of the quadrotor system just developed before, we can now depict in a graphical way the whole control system as we can see here on the slide. On the first line you have the roll, pitch and yaw angles, which are the desired angles, which are then in the attitude controller compared with the actual angles and generate the virtual control inputs U2, U3 and U4. On the other line you have the desired set value, which is the height, and this together with the altitude control will give a thrust, and then this can be transformed in the virtual controller U1. With the allocation method we have just seen before, we can then convert and transform actually these virtual controllers in the real value of the rotational speed of the 4 propellers, and the speed controller of the motors will then guarantee that the speed which is desired will actually be applied to the quadrotor in order to control it in attitude and altitude. In contrast to the attitude control, the altitude control, but also the XY control are typically defined in the Earth coordinate system. But on the other side, the virtual controllers are defined in the body frame. So if you look in the Earth coordinate system on our dynamic model of the quadrotor, we can easily find the equation, which is that the acceleration in z direction, the height direction, is equal to g plus the virtual control input u divided by the mass and multiplied by the cosine of the roll and pitch angle. This is actually the transformation from the body frame to the Earth frame. Now we can then define a virtual control in the Earth frame, which would mean that you define that the acceleration is equal to g plus 1 over the thrust you want in the Earth frame. Now we have the transformation between the Earth and body frame, and you want to control the height in the Earth frame. So you have a controller, a PD controller again, which you can see TZ, which is a proportional and the derivative of the Z movement minus the G vector multiplied by the mass, which is a fixed compensation for the controller. Now you can plug this into the transformation from the thrust to the virtual control, and you get the equation at the bottom of the slide, which is that the virtual controller is minus the thrust which you need for controlling your system at a certain height, divided by the cosine of the roll and pitch values. Now in hover mode you have typically very small roll and pitch angles, and so in a lot of cases you can actually even neglect these cosines and set the cosine of roll and pitch directly to 1. Finally, we have here an overall controller for our quadrotor. It consists of a position controller and attitude controller. It is a hierarchical controller. The outer loop is the position control, and the inner loop is the attitude control. So this is desired position in X, Y, and Z are given to the position controller. This position controller with 3 individual PD controllers calculate the thrust forces in the Earth coordinate system in X, Y, and Z. Through a transformation, you can then transform these thrust forces into the body frame of the quadrotor, and this gives you then the virtual control input U1, and in parallel it gives you the yaw and pitch angle, the desired yaw and pitch angle. Additionally, you have another input which is the desired yaw angle, which actually defines the orientation of the whole system. So the input of the yaw angle and pitch and roll go to the attitude controller, and this then calculates the virtual control input U2, U3, and U4. Now, through the control allocation matrix, this is converted in the control commands for the 4 motors, which then generate the speed control in the motors and control the quad in position, but also in attitude as requested by the user. Similar to the attitude control we have already seen before, also the control in XY position is in a first order model around small angles and around hover, fully decoupled in our dynamic model. So this means that we can again have 3 separate PD controllers for the position control, but in contrast to the attitude control, we have to transform the output thrust vectors coming from the controller back to the coordinate system of the quadrotor, because the thrusts are generated by the rotors, which are defined in the quadrotor coordinate system. If you do this well, you can actually do a very nice control of quadrotors, as you can see here. Here we have 4 quadrotors together, which are all controlled individually. So in principle, there is a 1 lead helicopter which carries the others behind them. All are controlled in attitude and height, but the main helicopter, which is the lead helicopter, is carrying the others behind to do a nice movement and collaborative transportation of this object.